All right, welcome back. Today we're going to bring together basically everything we've done for the last couple of weeks into one larger exercise that you're kind of in the middle of right now with your fifth hack and then going into your sixth hack as you start to add error checking and more rigorous unit testing with your hacks. Keep in mind we are on Piazza, we are on YouTube as well. So if you have any questions, all right, it's still on. So if you have any questions, please go ahead and post there. But otherwise, remember that this is the exercise that I introduced you to last time that we're going to do today. That we're going to write a function to compute change. So if we give you an amount from 0 up to 99 cents, what we're going to do is we're going to output the number of quarters, dimes, nickels, and pennies that you need to make change, right? So if we gave you 70.75, then we would expect back 3 quarters, 0 dimes, 0 nickels, and 0 pennies, right? Now, the only way that we can return multiple values is by using pass-by-reference variables. In this case, I'm going to have 4 pass-by-reference variables, buckets, where I'm going to put in the number of quarters, the number of dimes, the number of nickels, and the number of pennies. Then I'm going to use the return value to report an error. What happens when we're given a value outside that range? What happens when we're given something more than 99 cents, less than 0, right? We're going to check for those ranges, and we're going to return an error code instead of actually doing the work. So let's come over here. This is completely fresh, completely new. We'll do everything like you're doing right now in your hack 5 in a utils file, right? So I'm going to go ahead and create a new header file first. Let's see, new file, utils.h. And what goes into my header file? Do I put the functions in there, or do I put the function prototypes in here? So what should I call my function? Make change, or just change? Change is kind of not that descriptive. So compute change, make change, just choose one and go with it. Remember that in general, functions should be verbs. So make change. Change is already a verb, but it can also be a noun. So make change is a little bit more clear. And we're going to have to take some input here, right? Remember that prototypes end with a semicolon. So we're going to have to take some input here. The first input that we're going to take is the amount, right? Double amount, okay? And then I'm going to have to return quarters, nickels, quarters, dimes, nickels, and pennies, right? So int quarters. Why int, by the way? Yeah, you can't have a half a quarter, right? A half a quarter would be, I guess, a dime and 2 pennies, and then cut a penny in half, however that works, right? So I'm going to go ahead and go with an int. But should I just go with an int? That's a pass by value, or is that pass by reference the way that I've got it up there right now? That's pass by value. Can I make changes to it with respect to the calling function? Nope. I need to pass in a pointer variable. Right? So quarters. Then what? Dimes, nickels, and pennies. All right, there you go. Right. And I've already got my semicolon here. Okay? What's my return type going to be? Now that I'm outputting, again, I'm not really outputting anything. I'm giving you 4 buckets, and you're going to fill those buckets with the answers. And because we share those buckets, you're not actually returning anything. But I can now return something, right? I can return at most one thing. Should I make this a void function where I return nothing? No. I'm probably going to want to report an error message back. So initially, let's go ahead and make it an integer. 0 by convention is no error. Non-zero is some type of error. Okay. All right. Am I done with my header file here? What else goes in the header file? Documentation. All right. Documentation, and I'm going to use doc style comments. You should just get into the habit of doing it. /** with a vertical line of stars. This function computes it takes a given amount of money in the range 0 through 99, right? And computes the number of quarters, dimes, nickels, and pennies to make proper change, right? And we'll just assume that everybody understands what that means from the context, right? If you don't know what quarters, dimes, nickels are, maybe you could put in a link to the Wikipedia page on the American currency system or something like that. Returns a non-zero error code if ... What are some potential errors here? First of all, if it's outside this range, right? If the amount is out of range, or if ... We'll come back to that. What are some other potential errors that we might have to deal with there? Okay? Say what? Negative numbers? Oh, well, negative numbers certainly if it's less than 0, right? If it's outside that range. Yeah?
Numbers that have 3 digits instead of just...
Oh, okay, we could get really deep there. We could say that if you gave me 0.752, right? And then we could reject that or something like that. I don't want to go that deep, though, just for this exercise. But certainly, if that were part of the exercise, then yeah, we would probably want to round to the nearest cents. And if that rounded figure does not match the original figure, then we've got fractions of a cent, and we can reject that and return an error code. Right? I'm going to go ahead and make my utils.c file. This is the source file in which I put all my function definitions. Cut and paste my prototype, but instead of giving a prototype, I now give a function body with an opening and closing curly bracket. And you can kind of see here that this is a long line. One thing that you can do is you can break up these long lines by breaking up the input. And so this is a perfectly valid style as long as you are consistent about it, as long as all this stuff lines up. I wonder what a style would do with this. A style utils.c. All right, it's unchanged. A style likes it. All right, fine. You like it, I like it. All right. You can also break it up, 2 per line or 3 per line or something like that. There are no, hard and fast guidelines on that. It's just that the overall guideline should be avoid really, really long lines in your code. Okay. All right. Help me out. Do I repeat my documentation here? DRY, don't repeat yourself. Documentation belongs in one space and it belongs on your prototypes. What should I do though? What's the very first thing I should do? I need to include my header file. So do I include, or not include, utils, do I include source files? Almost never, right? I include what? Header files. Do I use the langle-wrangle for user-defined utilities? No, you can. It'll have the same effect, but it's bad style. The langle-wrangle are reserved for stdio, stdlib, math, right? The standard libraries, not your libraries. Your libraries, you should be using double quotes, okay? I can compile it at this point, by the way. It doesn't do anything, but I can compile it using the -c flag, utils.c, and it produces this utils.o file over here. There is something in there, right? In fact, it is 1,392 bytes. It's 1,392 bytes of nothing. There's this function. It takes these inputs. It potentially gives this output, but it doesn't do anything, right? And what else should I be doing when I compile? What didn't I put? The wall flag. That tells me that I reached the end of a non-void function. What does that mean? Make change. What kind of function is it? What kind of function does it, what kind of value does it return? An int. Do I return anything yet? That's what that means. I should be returning something, okay? So let's go ahead and write this function, and from now on, I will always be using the wall flag. Remember to do that. The grader does that, and if you've got unresolved warnings, it might compile, it might run, 100% correct. But if you've got warnings in there, that's a design issue, and points will be deducted for design, okay? All right, so what's the very first thing I do in my function? Remember, what's the whole point of error handling? Defensive programming. You look before you leap. So we need to look before we do anything dangerous. We need to do all error handling first. So if the amount is less than 0, 0 is fine because I can set everything to 0, right? Or if the amount is greater than 0.99, something like that, right? Or greater than or equal to 1, right? We could do that. Again, you make a great point about fractions of a cent. Maybe we can come back and do that if we have time at the end. But for now, I'll just go ahead and leave it like this. Return 0. 0 by convention is what? No error. This is an error. You gave me an invalid amount. So I'll return what? Say 1. Right? That's the first one I saw. Okay? What else? What else could be wrong with this stuff? What could be wrong with quarters? What's its type? It's a pointer, right? What's a bad pointer? Always remember what Bret Hart said. It could be null. So we do null pointer checks here. So if quarters is null, can I use it? Can I go like quarters is equal to, you get 1 quarter? No, what would I be doing here? I would be dereferencing a null pointer. Remember, Bret Hart will come out of the computer and hit you over the head for it, right? So don't do that if it's null. Check for if it's null. By the way, what else do I have that could be null? Dimes, nickels, pennies. So if dimes is null, or if nickels is null, or if pennies is null. Right? Now, if you want to get really fine-grained and say that I will return 2 if quarters is null, I'll return 3 if dimes is null, I'll return 4 if nickels is null. You can do that if you really want to. I'm not going to go that far, though, for this exercise. I'll simply return a different error code. An invalid pointer error. A null pointer error. All right? That looks pretty good for now, except for 2 notes. First of all, if you are going to do null pointer checks, you need to make sure that you're probably doing that first. In this case, it's not that big of a deal because I'm not checking the amount. Amount is definitely not a pointer. You don't have to check for null. All right? This does not make sense. Amount is equal to null. Right? Is amount a pointer? No, you don't check for null. It is a value. You check for values, not memory addresses. But if you were checking for quarters, it has to be not null, and it also has to be between 0 and 1. Right? Then you would have to make sure that you do that null pointer check first. Okay? In this case, it's not going to matter because I'm not even going to look at the values stored in these variables. Suppose that I did. Else, if quarters is, I don't know, negative, then return 3. Is that really an error condition? You gave me a bucket with a negative value in it. Do I really care? I'm the one computing quarters. You gave me 75 cents and a bucket with something in it. I'm going to say you need 3 quarters. Do I care what's already in that bucket? No, I'm going to throw it away and put 3 in there. You need 3 quarters for your change. So that doesn't matter either. Right? You have to think about what kind of errors are actually errors and what else is not an error, unless it's specified. Okay? Now, before we continue, suppose that we, to do, implement. Right? At the very end, once we've implemented it, what do we return as an okay, nothing happened, nothing bad happened, error code? Return 0 to indicate no, false, no error. Okay? And now I'll come up and do my to-do here. So I've got my amount, which is between 0 and 99. What do I do? Say what? So I need to compute how many quarters there are, right? This actually has me rethinking how to implement this and rethinking the design. And it goes back to what you pointed out. What happens when we've got 0.993, right? So we could reject that, or we could make that an impossibility, right? How could we make that an impossibility? Force the amount to be an integer instead, right? Now, that of course has changed my make change over here. If I were to try to compile this at this point, it would say, well, there are a couple of other issues here, but it's not going to work because for several reasons. One is because over here in my H file, I've got double, and over here in my utils file, I've got an integer. There's a mismatch here. This is not the same function as this one over here. I need to make them match. So I need to come back over here and I need to change this. Now, that solves a whole bunch of issues, right? That solves having to check to see if there's a fractional cent. It also makes the implementation a lot easier because now instead of looking at 0.997 and then dividing it by 0.25 and leading to a bunch of round off errors and a bunch of floating point errors and stuff like that, now it becomes crystal clear. I can use integer division. 75 divided by 3, that gives me 3. With a remainder of, how much more change do I need? 0. Right? That makes my life a whole lot easier. So let me come back up here and also change my documentation. And because the documentation is in one place, I only need to make one change. So 0 to 99. Right? And 0 to 99 if you want to not use the ellipsis there. Okay? Now come back over here, and if it's less than 0, or if it's less than, or if it's greater than or equal to 100, I do have to change that now. Okay. Orders, dimes, nickels. What else was wrong with that? I don't see anything wrong with that. So let's go ahead and try to compile again. It's griping about null because null is declared where? It's not in the math library. Where do you think it is? In the standard library, right? It's not input-output because you don't output null, you don't input null, right? It's in the standard lib, right? And up to this point, I've told you that it's the std lib is so standard that GCC will generally bring it in, and now, but it is still best practice to always include it. And now you see why it's best practice to always include it. Because in these cases where you're building a library, it's not automatically brought in. It's only brought in because main needs it. Right? Okay, good. Now let's actually compute how many quarters you need. Quarters is equal to the amount divided by 25. If it's 75, it'll be 3. If it's 76, it'll be 3 point something something something. Do we care about that something something something? These are both integers. Certainly, if I did that, then it would be non-integer, but this is an integer over here. So in any case, use integer division. Now, is that the correct way of allocating quarters there? Or setting quarters? Remember, quarters is a pointer. By making quarters equal to, say, 3, that means I'm making the pointer point to memory address 3, which probably doesn't even exist, much less belong to me. That's not going to work. So how do I make a pointer variable into a regular old variable so I can assign it a value? Star. That's the dereferencing operator. It's a reference. It's a pointer. We need to dereference it and make it into a regular old variable. Can I continue with this? Dimes is equal to amount divided by 10. No, why? Did I change amount? No, it was, say 75. Or let's say it was 85. 85 divided by 25 is going to give you 3. But does that change 85? Nope. 85 divided by 10 is now going to be 8 dimes. Right? So that doesn't work. How do I update amount to take into the account that I've already given you a certain number of quarters? I have to take the amount minus, yeah, go ahead.
Quarters times 25.
Quarters times 25, right? Why will that work? Now let's think about that in our heads. If it's 85 cents, right, just 85, then the amount divided by 25 is going to end up with 3, integer division, right? 85 minus 3 times 25 quarters is going to end up being 10, the number of the amount of pennies, or the amount of change that I still have to make. Okay. Good question. So, quarters. Is that a regular old variable that I can mix and match with subtraction, addition, multiplication? No. I have to do something like this. Now, that looks kind of weird because you're mixing, this is multiplication star. This is dereferencing star. It will work because of order of precedence. If it's a pointer and it's got a dereference in front of it, well, if it's any variable and it's got a dereference in front of it, it'll interpret it as dereferencing it. So I could do something like this, but it ain't going to work, right? Dereferencing something that's a regular old variable means that whatever was in amount, say 75 or 85 or whatever, it's going to jump to that memory location and try to use that value. Doesn't belong to me, probably doesn't exist. But best practice dictates that you probably should surround that with a parentheses. So that's a signal to yourself that, wait a second, this is not math, this is not multiplication, this is a dereferencing operation. Okay? You can do that on the left-hand side too, but it's not necessary because only one thing can be on the left-hand side. It's not as confusing, it's not as ambiguous. Well, continue in this way. Update the amount to be amount minus dimes times 10, right? And don't forget your semicolons along the way, right? And then nickels and pennies, etc., right? Before I go on though, is there a shorter way to write these things? Amount minus something, minus equals, right? Minus equals, right? Just a little bit shorter. Okay, nickels is equal to amount divided by 5. And then I update the amount to be nickels times 5. At that point, you've got the number of pennies, and you don't have to divide by 1. I mean, you can if you want to, but why would you? And so pennies will take on the remainder of the amount. Okay? So, does it work? I have no idea. Does it compile? You can at least answer that question. Yeah, great. Does it work? I have no idea. How do we go about deciding whether or not this thing works? We write some tests, right? That's where rigorous testing, automated unit testing comes into play. For those that have not fully read the handouts or watched the videos or anything, what is unit testing? A unit in coding is simply some indivisible piece of code, right? It could be a snippet, it could be an entire module or library. You can, for example, you could treat the entire math library as one unit, but usually our unit is a function, right? It's a black box thing. We don't know what goes on inside that function. I mean, we do know what goes on inside the function because we wrote it, but when we test it, we want to do black box testing. We don't know, we don't want to guess about what's happening inside of it. We're going to feed it inputs, and we're going to look at those outputs. And we're going to see, does that match our expectation? And that's what a unit test is. A unit test is a triple, right, you could say. It's an input, an output, an expected output, and an actual output. Right? Your code passes the unit test if the expected output matches the actual output. Right? Matches here in some way. Now, if these are integers, of course, you use equality testing. If the output is a string, right, then this string and this string, hello and hello, they should match. If it's hello and goodbye, clearly that they don't match. But if it's a floating point number, sometimes you have to build in a tolerance, like we've posted on Piazza. Lorentz time dilation, right? You could be, your number could be exact and match out to the 50th decimal place. It doesn't go out that far, but to the 10th decimal place. But in the 11th decimal place, it differs because whatever you used to compute the expected output was more accurate or less accurate, right? Or something like that. So you need to build in a tolerance. If these two numbers are within 1/1,000,000th of each other, then I'll say that's good enough and pass the test. So that's why we say matches. In fact, I'm going to put in matches there with a quote. Right? Generally, the expected output is computed using some other means. Right? Your calculator, right? An online resource, right? Wolfram Alpha or something like that, or like Lorentz time dilation. Maybe you did a Google search for Lorentz time dilation calculator online JavaScript or whatever, and you put in your inputs and it spit out an output. That's my expected output because I have reason to believe that that online calculator is correct. I'm going to trust it for now until I find that it's not correct, right? You can have false positives and false negatives. You can have false positives, right? Your test passes, but your code is actually wrong, right? Because it's wrong in the right way, right? You can have false negatives, right? Your test fails, but your code is actually correct, right? Your test may be wrong. Unit testing could be wrong in several different ways. Your input generally is not going to be wrong because it's just an input, but the expected output could be wrong because the calculator was faulty, or you fat-fingered it and you mistyped it or something like that, or you typed the arctangent instead of the arcsine or something like that, right? So that you could have false negatives, you could have false positives. So you do need to be careful. You need to go and find out what the issue is. Find out if the test is wrong or if your code is wrong and resolve those two things together. Very, very, very rarely are you going to get what would it be? False, positive, positive, negative, I guess it would be, where your code is wrong and your test is wrong, but they're wrong in exactly the same way, and therefore it passes, right? That's not going to, with very, very little probability that's going to happen. Unit testing is never a proof. Never provides 100% assurance that your code is correct. Only a high degree of certainty. Right? The more tests you have, the more certainty you have. Right? Tests should also cover your code well. Right? And what I mean by that is if we've got an error condition that checks for negative values, you'd better have a test that gives it negative values. If we have a separate error condition that tests for values that are greater than 100, you should have a test for that. You should have a test for every major eventuality. You don't need an infinite number of tests. Of course, that's unreasonable. But you need enough tests to ensure that every piece of your code, every line of your code is actually being tested at least once. Okay? So now that's what we're going to do. We're going to have a utils tester just like you're doing right now. Let's go ahead and create a new file, utilstester.c. And I'll include the standard input-output library. I'll include the standard input-output library. Why? Because I'm going to be telling you it passes or it doesn't pass. I'll be including my own utils library, right? Because those are the functions I want to test, right? Maybe the math library. I don't know. Right? Don't include things if you're not going to use them, right? So if you eventually find out, yes, I need to use the math library because I'm going to use that fabs function, fine, go back and include it. But be intentional about what you're including. Don't include unused libraries, right? Otherwise, you might as well just cut and paste every single standard library and put it in your code and have this big 1,000 lines of code of everything that you've ever included. Right? Don't do that. It's messy. Int main int argc char argv. Right? There we go. And by the way, it was asked last week, or maybe the week before, I forget. What does that mean now that we know pointers? So clearly that's a pointer. If I've got two of them, what is that? It's a pointer to a char, right? So we'll get into that later when, in fact, later this week when we start on arrays, right? We're not going to use that here though. Let's go ahead and test this function. And I'll go ahead and remind myself that that's what it looks like. Make change, we're give it an amount, quarters, dimes, nickels, and pennies, okay? So let's go ahead and create some variables for all that stuff. Int amount. Right. Here's my first test, the first one that I was giving to you, 75 cents. Right. Remember that it's an integer. I'm going to go ahead and call make change, and I'm also going to capture the error code. Right. Error code. Right. Error code is equal to make change. Okay? And I'll pass it in the amount. I'll also pass in quarters, dimes, nickels, and pennies. Do I have those variables though? No, not yet. Okay, so let me go ahead and create them, maybe. Int, they are pointer variables, right? So int quarter q, int d, int n, and int p. Yeah, where are they pointing to? What are they pointing to as of that right there? Null, garbage, dead beef. Remember that? Dead beef. That's a good. These aren't mnemonic devices, but they're ways of remembering things. If you're pointing to dead beef, right? Put on your vegan hat and say, "I'm not going to eat that. I'm not going to dereference that." Right? So I need actual real variables. Int q, d, n, and p. Once I've got actual variables, how do I make them into pointers so that I can pass it like a bucket? Ampersand, 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 and ampersand. All right? If I pass in 75, what are my expectations? Q is 3, and the rest should be 0, right? So let's go ahead and write a test case like that. If Q is not equal to 3, or D is not equal to 0, or N is not equal to 0, or P is not equal to 0, there we go, then the test fails. Right? Those are my expectations. If any one of them is wrong, then I can print an error message that says it fails. Printf error or failed, right? Right? And you can be more fancy about this, just like we are on the grader. We echo the input and we echo your output. You gave us blank, and we expected this, and that's just there to help you, help guide you, and help you. Oh, okay. Well, I need to use those as test cases for my own stuff here, right? But failed, I'll just put in failed for now, right? You can be, I'll put in a to-do here, to-do, be more verbose in my input-output. Otherwise, what happens? If it didn't fail, it passed. Okay, there's my expectations. What else should I be testing here? Well, here, let's go ahead and bring all this stuff together, and let's actually test and see if this, at least this one test case works. I need to compile the utils.c file, gcc utils.o and utilstester.c. I'm not using the math library, so that's not necessary. But I should be turning on all my warnings so that I know if there's any potential issue. There is unused error code. What does that tell me? What's that screaming out to you? You tested all the values, but did you test whether or not the error code was correct? What's your expectation here? is not, this is a correct input, right? So I would expect no error. So I would expect the error to be 0. And if it's not 0, then it's wrong. Right? So now let's come back here and that warning goes away. Think it's going to pass or not? I think it will pass. Yay. Right? Again, I'm going to be more verbose when I come back to this at some point. And, okay, great, it passed. What passed? Which test case passed? The one with 75 and it came up with 3000 and the error code was correct. Right? So I'm going to be more verbose about that later on, but not right now because we don't have, well, we could if we wanted to, but I wanted to get to other stuff here. Right? What else should we be testing? Is that it? Just one? Right? Yeah.
The end cases, like 100 or 0.
Okay, those corner cases, the edge cases. What happens when I say make the amount 100? What are your expectations? 4 quarters? Careful. What was our contract, so to speak? 0 to 99, right? If it is greater than or equal to 100, then we could give them 4 quarters, right? They're at an arcade. Arcades don't exist anymore, but let's suppose that I wish they did. Right? Right? So, 100. What would I expect? Would I expect anything about quarters, pennies, dimes, nickels? Right? Probably not. Should I even be looking at these things? No. What kind of error code do I expect? Right? Whoa, how did you remember that? Skills. Good memories, right? That illustrates another issue that we got into last week, right? What are these things called? 1, what the hell is that? 2, what the hell is that? 0, oh, okay, that's false, right? How could I have improved this code to be more readable? An enumeration. Type def, enum. These are going to be my error codes. Right? Error code, because there's only one of them. What's the first one? Okay, invalid range. Okay. What was the other one? Null pointer. Error. Is that all the errors? Remember, an enumerated type starts at what value? They're just integers. So Sunday, Monday, Tuesday, what value is Sunday? 0. And by convention, 0 is the no error. And now that I've got these, I can use them in my code. I don't return an integer anymore. I return an error code. To come back and redo these. I return an invalid amount. Oh, did I call it range? Oh, okay. There we go. Invalid range, null pointer, right? And no error. And then over here, what's your expectation now? Now you don't use 1, you use invalid range. If it's not equal to that, if for some reason we gave it 100 and it returned a null pointer error and we were expecting an invalid range error, right? That's something wrong with our code and we need to fix it. What else should we test? Okay, let's test the null pointer. Doesn't matter what the amount is. What should I pass in for, say, quarters? Null, right? And explicitly passing in these nulls. And I'll go ahead and go null. If you wanted to, if you wanted to be more rigorous about this, you would actually have 4 test cases. You'd have one where you put, in fact, if you want to, you can have all combinations of this, right? So for a null for the first one, valid for the other 3. Null for the second one, valid for the other 3. ... null for the first 2, valid for the second 2. Null for the first 3, valid for the second one. 4, well, it's going to be 2 to the 4, so that's like 16 test cases that you could use. Don't worry about that. I'm not going to get that fancy. This is as much as I want to do, right? So if it's a null pointer, If it's not a null pointer, then it failed. Right? And again, to be more verbose here. At this point, I've got how many test cases? Does anybody remember how many I've written? 1, 2, 3, right? Oh, what's wrong here? It failed. Right? What happened? Null pointer, null pointer. I don't know what happened. Let's find out. Right? If quarters is null, or dimes is null, or nickels is null, or pennies is null. So is this one of those, do you suspect my code is wrong? Is this one of those false positives? Your test passes, but your code is actually wrong. That doesn't sound right because my code is actually failing. Or is this one of those false negatives? If I had been more verbose in my input and output, I could see what's wrong immediately. Here's a hint. Amount is still 100 at this point in the program. What are you checking for when you come into this function first? You're checking the amount first, in which case you give an invalid range. That's perfectly valid, right? It is failing that test, but it's also failing another test over here. So what I need to do is I need to make sure that amount is a valid value, and then isolate the tests for these null pointer errors. And, oops. Now that false negative has been corrected. My test case was wrong. Okay. Unit tests, each one of these unit tests, you can collect them into a test suite. Each one of them should be in isolation though, right? Our choice of inputs for one affected the outcome of another test. If we had used a more formal testing framework, like you'll use this week in your lab and your hack, called CMACA, then you don't have to worry about these details. The framework takes care of it for you, but at a cost. The cost is that it's much more complex to learn. Right? Another thing that it provides you is 1, 2, 3. I just want a summary. I don't care that they all passed. I just want a summary. Did I get 100% or not? Right? And to do that, you should probably also have counters. Num correct, num right, and num wrong. Right? By the way, what value, how many have you gotten right so far at this point in the program? 12? Well, no, at this point, on line 12, sorry. We haven't done any tests yet, right? 0. Is that what's stored in that variable right there? No. Not necessarily. Remember, dead beef. Make sure that you are initializing your variables. Int num wrong is equal to 0. And now I can come back down here, do a lot of cut and paste. Num wrong plus plus. Right. For that one, and for that one. And then num right plus plus. For that one, and that one. Lots of boilerplate code that is taken care of by the unit testing framework like CMACA. You don't have to write your own. You basically just come up with those 3 elements: the input, the expected output, and then the function that you want to test and how to call it. And then it takes care of verifying everything is correct for you. Okay? And it also takes care of a summary. Printf, percent correct, or right, percent %d, and the line, num right, oops, wrong, num wrong. And then if you want to, you can print out a percentage. Printf percentage. Right? This is also your grade, incidentally. Right? We do eventually grade on just a percentage. Correctness, they got 75% correct. Okay, that's the grade. 75 times 16 points for correctness, we're done. Right? Makes it so much easier to grade as we move along to more complex stuff. So num right divided by the total, which is num right plus num wrong. By the way, if I do it like this, what grade am I always going to get? Oops. Yeah, ignore that. There. Ignore that. What am I going to get? 0, even though they're all right. None of them are wrong. I got a 0 percentage. What did I do? Yeah.
You can't compute in that spot.
I can. If you want to, you can go ahead and move this. If that unnerves you, you can put it into another variable here. Percent is equal to this. But ultimately, what's wrong there? Yeah. Integer division. So let's make one of those things a double, and the other one can remain an integer. It would probably not be ideal to just make them all doubles. We've seen this before where people think, okay, I ran into integer division. I hate integers. I'm going to make everything into a double from now on so I don't have to think about that. That's not the best solution either, because then you get into integer values that are and round off errors. 1 divided by 3. If I take that value 1/3 and add it 3 times, 1/3 plus 1/3 plus 1/3. In mathematics, what is that? That's 1. In code, it's not. It's like 0.9999999. And then at the very end, it goes down to 8 somewhere. It's not, you have floating point errors and lack of precision because you can only represent 16 digits of precision. Right? So 1/3 times 3 is not necessarily 1. So it is a good idea when you need exactness and precision and it's an integer to use an integer. Now let's go ahead and that warning goes away, by the way. That's what it was warning me about. And run it. And now I've got a 100%, but it's 1. So if you want to, we can also do what? Multiply it by 100. And then it's now it's really fancy. I only want to get it out to 2 decimal places. Great. Formatting this really nicely, right? Except that I also want it percentage. Let's find out if this works. Nope. What's wrong? Percentage is used as a placeholder. So how do you think I get percentage? How do I get it to print the actual percentage? You can escape it for one. This should work. Nope. Sorry. See, in many languages you can do that. Java allows you to do that. Put 2 of them. There we go. And now you can get that percent there. So if you want it, if you really want it to, you don't have to. It's just, if you like twiddling with these things and getting it to print exactly how you want it, great, good for you. Make sure that it's correct before you start adding this polish on it, right? All right, questions so far? No? What other test cases would you do? Well, if you just cut and paste, you can start seeing, whether or not it actually works. So go ahead. Yeah.
Negative numbers?
Okay, so negative 50. What would you expect there? Not a null pointer. Out of range? So what was it called again? Invalid range. Okay. And I probably don't want, I want to test an isolation here, so I would want to probably restore valid pointers to it. Right? Not that it's going to matter in this particular case, but it does matter overall. Still 100%, great. Anything else? Again, copy pasta. In this one case, when it's all boilerplate code like this, I'd say that that's one instance in which you could probably get away with committing that copy pasta sin, right? What else? What about 99? What would your expectations be there? It's not going to be an error code anymore. It's going to be more like this up here. What would your expectations be for 99? 3/4, of course. That leaves 24 cents. So how many dimes? 2. Okay. How many nickels? We're up to 95, so 0. And how many pennies? 4. Okay. Let's see if that works. Yay, it still works. Right. And again, you would want to be more verbose about this. You could print a message here, printf testing make change on percent F quarters, nickels, or dimes, nickels, pennies equals percent, actually dot dot dot, and not percent F but percent D amount. There we go. Testing dot dot dot, and then it failed or it passed. And you can kind of see here what it looks like. Testing this, it passed. If it failed, then you could output, here was the input, here's the expected output, here's your output, and then that gives you a way to start debugging. And debugging is very, very useful. We'll use a tool called GDB to do that after the midterm, or during the midterm week, I forget which one. Right? Okay, any more? Otherwise you can just, if you just cut and paste, you can make as many as you want. I think we require at least 3 per function, so you need at least 9. But you can go more, right? What's another edge case here? 0. Is that valid or invalid? That's valid. You would expect how many quarters? 0. How many dimes? 0 nickels and 0 pennies. And great, I'm still passing. Right? Now, why would you want to do this again? Right? What if I found a bug and I needed to go back and make a change? Right? I was dividing by 5 here instead accidentally. I would have to then come back and retest all of those other values. And if I was doing this in an ad hoc way with like an interactive program or command line arguments, I would have to look at my list of tests that had passed previously and go down the list, test them all again manually. But if I'm writing a unit testing framework like this, then all I have to do is compile, run, as many times as I want, and it's all automated. Great. Now, a formal unit testing framework like CMACA, or any language will have some sort of a unit testing framework or library or something like that. It makes your life even easier because then you can just hit a button, right? And you don't even have to do this boilerplate code with specify, with error messages or coming up with a nice little summary at the bottom here. Okay. And you'll use that tomorrow in your lab 6, I think, right? Yeah. All right, questions on that exercise? Yeah, go ahead. Oh, crap. Actually, no, it's in labs. Okay, so it's git clone github.com me, and then it's the sixth lab, or okay, 155 C lab 06. Okay, there it is, and I believe the README is not going to have anything in here. But I think that you could just, I'm going to have to look at my make file here. So here we go, color utils tester CMACA. So make color utils tester I guess I need to be in that lab, CSE lab 6. Make that, and it takes care of it for you. Now, obviously, I've not written any of those functions, so to sepia, to grayscale, it's not returning anything, so it's going to give me warnings, and all of the tests are going to fail. 68 failed tests because I haven't written any code yet, right? But that's how you use it. That's how you compile it, use it. If you're interested, you can take a look at the make file and see how it does it. It just includes -L, like -LM would include the math library. This is include the library called CMACA on the system it's already installed, et cetera, et cetera. And then it'll build this color utils CMACA. Don't worry about workaround, we don't even mention that. That's how you build and use it. Now, how do you write your own if you really want to? I think that you have to for hack 6, but not for the, well, you might, I think, yeah, you have to for this lab as well. So let me open it up. Where is it? see mock, I need more room. There we go. All right. So just using this as a, you're reverse engineering this. Look at the ones that we've already built. We've built 68 tests for you already. You only have to do a few more. So for example, let's test sepia out of bounds. That's all taken care of for you. Sepia values here, right? So you don't have to worry about this function. It's already done for you. Let's take a look at the main with examples here. Oh, wow. I think that was somebody else that did that. That was Hunter, I think, a long time ago. There we go. So where are the actual values here? Okay. So these are the general tests. These are the RGB values. These are inputs. This is your mode, the average, or the lightness, or the luminosity. And then these are your expected outputs. So how would you go about using this? Okay, I'll just add one more. And then 41, 18, and 2. Then pull out your calculator and decide what the expected output would be here. I don't know because I don't have my calculator with me, but you'd put that in there. All right. And I think that you would, yeah, it'll take care of everything else for you. So you can add your own. There's some other examples here. Those are grayscales, those are sepia, min and max, but I think that those are all pretty much covered. I think here's the min. We give 10, 20, 30 as inputs, and then the last one is the expected. The minimum among those is 10. But otherwise, the comments should tell you what the expected results are. I don't remember whether or not we require you to add your own. Don't quote me on that, but you can easily add your own in this. And then for hack 6, I think we give you a starter file, do we not? If not, email me or post on Piazza. I'm going to have to remind myself. And then you can use that and follow how we did it. Does that answer the question, or do you want more? Because it's going to require covering arrays to really understand what's going on there. These are all arrays of arrays, and so this is an array of values, and then it's an array of multiple arrays, and then what we do is we go in. No, we don't go into a. Oh yeah, we don't go into a loop here. We just add on to these. Right, so if you add another test case, you'd want the 57th. Usually you'll add them to the bottom or something like that, not somewhere in the middle. And then there's yet another test case. Of course, I would need to write that. All right. And then, well, whatever. Yeah. No other questions? Okay. Then I'm okay with ending it right there. Otherwise, what we will do is we'll start getting into arrays on Wednesday.